Okay, and now we are joined by Jessica Libby-Roberts, who is a grad student at CU Boulder working with Dr. Berta-Thompson on research regarding exoplanet atmospheres. She currently works on super puffs, planets with densities similar to cotton candy. Her research tries to understand how the low gravity of these puffy planets holds on to a substantial atmosphere and what that can tell us about planetary formation and dynamics. Jessica, thanks so much for being with us.
Thank you for inviting me. I'm really happy to be here.
Well, we're really happy to have you. We'll start right off with a question that is important to know the answer to for the rest of this episode, which is what is an exoplanet and how do we find them?
That's an excellent question to start with. So exoplanets are just planets that orbit other stars outside of our own sun. So far, all of the planets that we have found have been in our own galaxy. So right now, exoplanets are Milky Way planets. I don't know what we'll name those planets when we eventually find them in other galaxies. And
Exoplanets.
yes, and we find these actually by several different methods. The first one is known as the radial velocity method, which is this idea that as a planet orbits its star, it's going to tug on the star as well as the star is tugging on the planet. And this tugging on the star causes the star to actually orbit the center of mass of the system. And so this orbiting of the star, you start seeing the star move far away from you and close to you. And this sort of gives you a shift. When it moves away from you, you see what's known as a redshift. The light becomes longer. This is the Doppler effect. And as the star moves towards you, the light becomes blue shifted, or the wavelengths become more compressed. And that's how you detect whether there's a planet there. Another really common method that both the Kepler Space Telescope has used and TESS, which is currently orbiting right now looking for planets, is the transit method. So this is the idea that as a planet passes in front of its star, it will block a certain amount of that starlight. We see that starlight as a little dip in the brightness, and we infer that there's actually a planet there. And I think there's a couple other techniques, but what I think is sort of a really cool way of finding planets is we just image the planets. So we take a coronagraph, or something that a fancy name for something that blocks out the star, and we look for the planet's light. So if you imagine a total eclipse, the moon moves in front of the star, and when that happens, you actually see other stars around in the day sky. And so that's the same idea, where we can actually see a planet. So I'd say there's several other methods, but those are the three main ones.
Nice. So we've got radial velocity, which is where the star is kind of wobbling in place as the planet orbits it, and we watch that wobble. We've
Yes.
got the transit method, where the starlight, we kind of see its shadow in a sense, right? And as the planet crosses in front of it.
Hmm.
And then we have, did you say it's the coronagraph, or we're blocking the starlight, the center of the star, and we're looking around that for the planet, like actually taking a picture of the planet.
Yes.
Cool. Very cool. And I imagine that's really difficult to do and would require like very high sensitivity instruments,
Oh,
considering that these are very far away from
yes. It's
us.
incredibly difficult. Stars are very bright. Planets are really faint. So you need to find really big planets that are really hot. So normally, newly formed planets, right? So if you imagine trying to form a planet, there's a lot of energy. And so if you can find a planet that's really big, that's really far from the star and really hot, those are the ones we're seeing.
And I think that this isn't always intuitive to people that are like, kind of new to these conversations. But just to be extra clear, the planets are not really giving off any visible light, right? We're only looking at starlight, and then the planets are basically these dark objects that we don't see them directly, other than in that imaging where we kind of, I assume it kind of shows up as like this black dot, where it's not, we're not looking at these bright objects like we can look at stars in the night sky.
Yes, we tend to image planets in the infrared,
Okay.
which is wavelengths longer than visible light. That's essentially, infrared is like looking at heat signatures, and so
Okay.
we are able to observe. But you're right, in the visible light, we don't see the planets themselves.
Cool.
It's very difficult in that sense. And then in the other two methods I mentioned, we never actually see the planet. We are looking at how that planet is affecting the light of the star.
And that's because the star is easier to observe than the planet itself, right? So
Yes,
then we can
that's
say,
right.
oh, well, that star is easy to look at. So what can we learn by looking at that star? Very
Yeah.
cool. Very cool. All right.
All right, so planets are super hard to find. So then how exactly do we go about studying atmospheres of these planets that are so hard to see in the first place?
Again, we have to look at how the atmosphere affects stars' light. So atmospheres can come in many different flavors. We've already seen that in our own solar system. We've got atmospheres around those rocky planets, and we have atmospheres around things like Jupiter and Saturn. And we see that also in exoplanets. So right now, while we would love to determine atmospheres on rocky planets, we can only really observe atmospheres around gas giants, just because there's so much more atmosphere, so a bigger signal that we can work with. So talking about atmospheres, it can come in either terrestrial or gas giants, but for now, let's talk about gas giants. And the idea for this is that as a planet passes in front of its star, it blocks a certain amount of that starlight. But some of that starlight is actually going to be filtered through the atmosphere itself. So we use a technique called spectroscopy, and this is just looking at individual wavelengths of light. And atoms and molecules absorb a certain wavelength of light, and it's very specific to that molecule. It's like a fingerprint. So when we look at different wavelengths of light, and we notice that this one wavelength is being absorbed, or that we're not actually seeing that wavelength, we can figure out, all right, we know the wavelength, so what molecule must be blocking that light? And this gives us a sense of what is actually in the atmosphere of those planets. We've seen water and carbon monoxide are the two big ones. We're currently working to find methane, but these are sort of the three main molecules that we are detecting at this point. And we know that the James Webb Space Telescope, or JWST, when it launches, it will actually be more tuned for finding more molecular species. Right now, when Hubble launched, we didn't even know that exoplanets existed. So we're sort of relying on manipulating like old instruments to look at exoplanets. But JWST is made for looking for exoplanets. So I'm excited to finally see these. But yes, we have to observe the star's light interacting with the atmosphere in order to detect what's going on there.
So on a related note, what is sort of required for an exoplanet to have an atmosphere? Do we know, is it the same sort of like rules that we have for atmospheres on planets here in our solar system? Or is it completely different, or we have no idea?
It is a hotly debated topic, which you would think would be surprising. It's we know that gas giants, so Jupiter-sized exoplanets, have an atmosphere, and we know this because if you look at their bulk density is less than rock, so it must have some type of hydrogen-helium atmosphere. But as you move to smaller and smaller planets that have less gravity, there is a debate on how small a planet can be and still hold on to its atmosphere. Or so we're finding exoplanets are closer than Mercury, but could these exoplanets maintain their atmosphere if they're big enough? So if you took Earth and moved it inside Mercury's orbit, could it hold on to its atmosphere? We don't actually know.
And
So
is that a
this is
question because the star might pull the atmosphere away from the
yes.
planet? The gravity of the star is powerful enough to pull the gas away from the planet?
So two things on that. That's excellent. We have actually detected that a star is consuming the atmosphere of a planet. And another one is that the stellar wind and flares could just push the atmosphere away, blow it away, just like we're seeing on Mars. I believe we had a podcast earlier on that one. And as it blows, like Mars blows the atmosphere away, can it still hold on to anything? And we don't actually know yet.
And it's not unusual to see these really small systems, right, where these planets are quite close into their stars. It's not, every system is not like ours where it's spaced out the same way and stuff is the same size. It's kind of like people, we see things in all shapes and sizes and, varieties of all sorts.
Yes, I mean, luckily, all planets seem to be coming in the same shape, but
I
sizes
like to
are
imagine a cube planet. It's a planet, it's the same as Earth, it's just a cube. That's it.
a board cube there.
So,
But you're right. They could have. There are no systems that we have found like our own solar system. They're all different from what we can find, which is amazing.
so speaking of, this large variety of in what we see in other planetary systems, something that you study particularly is what we call super puffs. Can you tell us a little bit about that, term and what we're talking about here?
Yeah. Oh, I could talk forever on super puffs. They're my favorite. So super puffs. I'd say so. When Kepler, I'll tell you the story of how we found them. When Kepler launched, it discovered thousands of these planets, and what we found are planets that aren't actually like our own solar system. In our solar system, we have the rocky small planets, and then we have the gas giants. And Kepler discovered that there are planets that are super Earths, rocky planets that are bigger than the Earth, but smaller than Neptune. And another term we use is sub-Neptunes, which are small gas giants. And these seem to be very common. But then they started discovering these really large exoplanets that are the size of Jupiter. And that's not unusual. The size of Jupiter is great. And there's one thing about the transit method that we're limited to. We can only detect sizes of exoplanets. We only know how big that shadow that's being cast is. We don't know how massive that planet actually is. And so we use radial velocity is great for this. It tugs on we see the planet's mass tugging on the star, and that tells us how massive that planet is. But we're only limited to very bright objects for radial velocity. And so a lot of the Kepler targets are faint. So we use a different method to get the mass, and that's this idea of transit timing variations. So if you have one planet, you would think that as it orbits the star, it would cross the star or transit the star at the same time every time, right? So Earth, 365 days, we would cross every 365 days like clockwork in front of the star. But when you have other planets, they interact with each other. They tug on each other with their gravity. And so the planets actually show up a little bit early or a little bit late, on the order of maybe 30 minutes. And we can detect this change in time. And so it tells us that there are multiple planets in the system, but also the masses of those planets tugging on each other. And so what was interesting, in particular, this one system, Kepler 51, it had 3 Jupiter-sized planets. And when we looked a little bit closer, we noticed, or I should say, Kento Masuda at Princeton University, he was the one that actually found these planets originally. And he discovered that they tugged on each other, and that gave him the masses. And what was so surprising about these masses is that they're Jupiter-sized planets, but they had 1/100th the mass of Jupiter. These planets are an order of, say, 4 or 5 Earth masses instead of 300 Earth masses, which is just weird. And so this discovery went out in 2014, and for the most part, it was I wouldn't say dismissed, but it was just so mind-boggling. Like, could we actually get the numbers wrong? There must be something. I mean, we're talking about densities. So when I calculated, the densities are about less than 0.1 grams per cubic centimeter, which is the density of cotton candy. So Jupiter-sized balls of cotton candy. How do you explain this? And so that is just something we weren't sure about. And then we started to find more of these planets. We started to, I believe there's probably like 10 to 20 of these now. And so they're common. They're not common, but they exist. It's not a fluke. And so what I've been working on is trying to figure out what could be in the atmosphere of these exoplanets. And so I've used that idea of spectroscopic during a transit to look through the atmospheres of these planets. And what I discovered is for the Kepler-51 planets is there are no absorption features at all. There is no water that we can see. There's no carbon monoxide. There's no methane. There's nothing. And this is really weird because we know there must be something in this atmosphere. You can't have a ball of just hydrogen and still maintain this planet shape. So what we thought was, well, maybe if you put like a high altitude haze layer, so picture Titan, right? You can't see the surface of Titan. It's just this blocked out haze layer. And if you put it up high enough, all of that water and methane signatures underneath it can't get out. So somehow, and we're still working on figuring this out, but these planets with their very low gravity and low densities are maintaining sort of a cloudy haze layer on the top of these atmospheres. And yeah, so we don't know why or how, but that is what we found for those planets. And then I believe there are being looked at other super puffs and finding some similar results. So maybe super puffs are just really cloudy.
There seems like a ton to unpack there when you see this new
Oh,
thing.
yes.
That's like it, because it's one of those things. Astronomy, I think, is in physics are notorious for doing this, just completely shattering human intuition and saying, well, it can exist, so it does. And then we have to try and figure out, what are we looking at? What's going on over there?
Yes, exactly. And the funny thing, and the reason why we want to figure out water and methane and everything in the atmosphere is because we have no idea how these planets formed. They go
Right.
against everything we know about formation. The general idea, in a nutshell, of formation is that you need to have a core mass of about 10 Earth masses in order to start really accreting and holding on to an atmosphere. But when you have 4 Earth masses, your core is probably like 2 Earth masses. How does Earth become, like, imagine an Earth somehow managing to accrete enough gas to make it the size of Jupiter? We just don't know.
Do
And
you think
so
that this has the potential to change the way that we think about planetary formation in the long run?
I think it definitely will probably not completely change our theory, but we have to have an add-on. There's more
Okay,
details that we're trying to uncover. And so that's what's really exciting about these planets.
got it.
So recently, I saw an article talking about the puffiness of these planets might be due to them having this large, extensive ring system, like Saturn, but on steroids. Have you looked at any of this? What's your thoughts on this?
I have looked at this, and I think it's a very interesting idea. And I think it does a great job of explaining some of these super puffs. The idea with the ring system is that if you imagine looking at Saturn sort of face on, so you have the ring in this, or the planet in the center, and this giant ring around it, and you pass it in front of the star or our sun, it's going to look a lot bigger than what the planet actually is the idea. And I think that's a great idea for some of these super puffs, and it would explain why we're getting these flat spectra for these planets. But I do remember in that paper they did discuss that they could only use that ring system. A ring system like that would only be stable around some of these planets, not all of them. And also, you would have to have all of these planets, you'd have to believe that all these planets just happen to be aligned face on. And so while I think this might actually explain some of these super puffs, it probably doesn't explain all of them. And my guess is we're going to need multiple explanations to explain all of what's going on.
Does the math check out if you assume that it is just a mega ring around all of these planets, and you then redo, okay, imagine we had a planet that was this big because the ring made it look that big, and then you did the density calculation, does that make it work, or is there still even a discrepancy at that point?
You could make it work, depending on the size of your ring. So there's two things that come into play. It's the size of the ring. How big of a ring do you need in order to make the density more Jupiter-like? And then the other question is, can you maintain a ring that large? And so for some of these super puffs, you can, and for others, the stellar wind again would probably evaporate some of this ring, and so you couldn't dynamically maintain this large ring. So it does check out for some of these.
So thinking about this now, and I don't want to get too technical with this, but like Saturn and all the planets in our solar system that have rings, except for Uranus because it's wonky, the rings are in the same orbital plane as, the same kind of flat disk as the planet is going around the star, right? So they're all kind of in this line. But if we're looking at these planets going around their star and the rings make them look bigger, that means they would be essentially tilted on their side.
It'd essentially be Uranus.
That's weird.
Yeah, it's very weird.
And that's unlikely, right? The way that we know how planets form, that would be exceedingly not expected.
Right.
If it were to be anything like the way that we think that solar systems form.
Exactly. That's
Unless
why, yeah. And
right.
Again, I mean, we have Uranus. It's in our own solar system, so we know it's possible. But the question is, how likely is that to actually have occurred?
What if the 10 or 20 or so super puffs that we've seen are just those 10 or 20 examples where it is the weird situation where it's on their side? And then there's actually tons of other planets like this that we see, but we don't see it this way because they're normal and we see them, edge on. Is that a possibility, do you think?
That is a possibility, especially, again, depending on if you can maintain a ring system and tilt it on the side. So I think maybe about 5 of these, I believe from the paper, about 5 of these could be explained with a ring system. And so it might be possible if you think about, we know 4,000 of these. What if you just, 5 out of 4,000 maybe? So, I should say we know 4,000 exoplanets, not 4,000 super puffs. Let me clarify
Right,
that.
sure,
So,
sure.
so maybe we honestly don't know enough about planetary formation to say one way or the other.
So exoplanets are a relatively new field of study, and I'm sure it's rapidly evolving. It sounds like even just in the work that you've done, a lot has kind of been uncovered maybe. Does that make your job more difficult or more exciting or both or neither? Tell us about the pace of what you study.
It's definitely more exciting. It is kind of funny because when you read papers and you look at how long ago those papers were, sometimes you're like, oh, that was published way back in 2012. Things have changed by then. And then you realize it's only been 8 years. Whereas other places, such as like people that study the sun, cite papers back from the 70s, which just is incredible to me to have a paper stand up for that long. So it is an ever evolving field. And it means that what makes it so exciting is every time we make a discovery, there's like 20 questions that come out of that one discovery, which means then we have to go explore more. So I wouldn't say it's difficult. It just is, you never know what you're going to find. And so it's always a rapidly evolving system. I know when the super puffs first came out, we announced our atmosphere finding, and all of a sudden there are multiple papers in the last year, and it's only been a year that have come out of explanations of what could be going on. And so I do love that about this field, is it's just keeps you on your toes.
Well, yeah, it's an interesting point that you bring up about, thinking, oh, this paper was published 8 years ago. It's probably no good anymore because everything's changed in some fields. And then in other fields, you can have a paper that's been around for 40 years and it's still like, what we all learn from. And that's something, kind of funny that there's a textbook that I use for one of my classes. It's the Carolyn Osley astrophysics book.
Ah, yes.
And that hasn't been updated since like 2007. And so part of me is like, well, most of it's probably fine, but also that's 13 years of new discoveries that aren't being included in this textbook that's supposed to teach you like the fundamentals of modern astrophysics. So it is kind of interesting to think about, how can we update everything so that it's current, when we make these discoveries.
Exactly. It's why it's very hard to make an exoplanet textbook. They've been made, but it's always changing and updating when you read through those. And not to say like a paper from 2012 isn't good. It's just we've learned so much more from that, where you just keep following like, all right, they started it, but where are we right now? And so it's kind of fun to see how that traces out.
I wonder if we'll get to the point in exoplanet knowledge where a like solid textbook would be viable, like to say, this textbook, we know enough about exoplanets that now we can actually write a text and it will be definitively correct for at least a little bit. And we're not going to have new discoveries in the next 20 years that, make it wrong. Do you
That
think
will
that's
be a while.
Well, that's so crazy that it's such a young science. That is so cool.
Yeah.
Right,
I mean,
because
we're discovering planets. Sorry. Go ahead, Tara.
Oh, no, I was just gonna say, because the first exoplanets were really just discovered like in the 90s, which to me is like yesterday. I know it's 20 years, 30 years ago now, but
Yeah. And we're discovering planets every day. So it's always going to be changing. But I guess that's kind of science in general. So it's kind of fun.
yeah. From like a geologist standpoint, it boggles my mind that things are so new. I'm looking at things that are like millions of years old, and we're talking about planets that we only know about for the last like year. That's
Yeah,
crazy.
exactly.
So, kind of on that note, looking forward, what sort of interesting things are coming up in the world of exoplanets that you're excited about?
Well, I know every exoplanet person is really excited about the James Webb Telescope if and when it ever gets launched.
Could you tell us just really quick the story of the James Webb Telescope? Why are we all laughing at that right now? Tell us why we're all laughing at that right now.
Yeah. So the James Webb Space Telescope was initially set to be launched, I believe in 2012. And it's this I forget how big it is. This has been so long that I've even forgotten this. But it's going to essentially replace Hubble, and I believe it's at least 2 times the size of Hubble. So it's going to have this ability to look and make precise measurements of rocky exoplanets, which the atmospheres around these, which is going to be amazing. But it was set to launch in 2012, and it got delayed, and we had to give it more money, and it got delayed, and we gave it a few more $1 billion. And it continued on getting delayed, and it's 2020, and it still hasn't launched. They're coming close. Like they've been announcing like it's passing its tests and everything like that. And so its launch date is currently for 2021. We don't know. I wouldn't hold your breath on that one. And I won't knock it too much because it is quite a feat in engineering. They are going to launch it out to a stable point on the other side of the moon. So it's going to be very far from Earth. If anything goes wrong with this telescope, we're not going to be able to fix it. We're not going to be able to do what we did with Hubble. And so we want to make sure it's perfect
from the get-go.
Exactly. And so at this point, we've invested so much money into it. We want it to be perfect. So there's a lot of technical stuff that is going into this, but we just laugh because you see textbooks and papers that are saying like, well, in 2012, we'll know for sure with JWST. And then obviously that hasn't happened. So it's kind of been a little bit of a joke in the exoplanet community, but I also know that we're very excited for it to launch because it will revolutionize exoplanet science again. I don't want to get too hopeful on saying that we could detect if a planet is habitable or not, but we should start being able to say whether some of these rocky planets have atmospheres. And that's a huge step for the future.
That's a big part of what we think would be, what's the word I'm looking for? Like if we saw a rocky planet with an atmosphere, that opens the door to many more questions about, life outside of our solar system, right?
Oh, so much more.
And that's something that is so inspiring to, scientists like yourself and students like myself. Everyone is like, wow, aliens, that's pretty cool.
Oh, everybody. Yes.
If you could visit any exoplanet, imagine that you could. What do you have one that you would want to just go to and check out for yourself up close?
It's actually kind of funny about this question because you did send it to me ahead of time, and I sat there for a while thinking on this one. And I know a part of me would love to visit the Kepler 51 planets, so super puffs, because I would just like to know what is going on with these super puffs. Are we actually on the right track? And I'd also love to see if they look like Jupiter. Do they have bands? Do they have colors? Things like that. And then I thought about it some more, and I realized that I'd really like to visit a rocky planet around an M dwarf, say Proxima Centauri planets that have recently been announced. And the reason I think I would love to visit one of these planets is try to picture, so an M dwarf or a red dwarf puts out most of its light, it's fainter, and it puts out most of its light in the red and the infrared.
And this is a
So
star, to be clear, not a
how
planet,
does a
right?
planet look when most of the light is in the red instead of the sun? Yes. Yeah. So a star is putting out so much light in the red. And if you're standing on a planet around the star, first of all, you'd be really close to the star to make it habitable because it's so faint and doesn't put out as much heat. You need to be moved in. So the star likely fills your viewpoint. But also, if you think about it, plants here are green. Our sun puts out most of its light in the yellow and green visible wavelengths. So what would plants look like around this M dwarf? Would they actually be red? I mean, this is hypothetical. If there were plants, would plants would be red? Or would they appear dark because they normally would look green, but because the star is not putting out that much green light, there's not that much light to reflect. So would they just sort of appear like a dark red color just because they don't get that much light? And then the other one I was thinking about on this planet is if you stare off into the ocean, our ocean is blue. It's this bright blue, green, and that's because water tends to scatter and reflect blue light, but it absorbs red light. And so think about being on the shores of this ocean around an M dwarf. Well, since water absorbs this light, this red light, then these oceans would probably appear black. So instead of this nice blue ocean, you're looking at black water. And then who knows what the atmosphere? Our atmosphere is blue again because nitrogen scatters blue light. But again, you don't have that blue light, you have red. So is the atmosphere's red, like a reddish haze, or are they black because that light is not being scattered? So it's just this sort of, you have to change your entire perspective of what it would look like to be on a planet around a star like this. And it just feels like it's straight out of, Star Trek or science fiction. And so I have to say, as interesting as my super puffs are, like getting this change of perspective would really, I think, be very magical, like a magical experience for me.
I like how much you thought about, initially you were like, oh, but the science, we could figure this out up close and personal. And then you were like, but wait, what if it was like just this completely different experience? Like you said, like sci-fi. And that's funny that you bring this up because Tara and I were actually talking about this, I think last week. I have the Curiosity picture, well, one of the Curiosity pictures of Mars. It's like looking back over its tracks into this valley as my desktop wallpaper. And there were two downloads. There was the white balance or the white point corrected so it looked like Earth's atmosphere. And then there was the one that's actually in Mars's atmosphere, and the colors are totally different. And so, that's a very cool thing to think about. That man, that's not even something that I think about really ever on a day-to-day basis of, here on Earth things look the way they do because of so many things coming together, the way our star is, the way our atmosphere is, and that could be totally different somewhere
Yeah.
else.
Yeah. It's kind of fun to play around and think about it.
Yeah, that's super cool.
Yeah. So switching gears a little bit, we always like to ask people, how did you sort of get to where you are now? Have you always been interested in exoplanets, or did you start somewhere else and kind of fall into this? Tell us a little bit about your story.
Yeah, so I was actually going to ask about this one because I'd consider my path a little bit more unique, not necessarily getting interested in exoplanets, but how I got to where I am. And I just want to take a moment to go into that. So I actually studied undergrad at Caltech back. I graduated in 2009, and I at that time I was interested in Titan and a little bit in exoplanets, but exoplanets still weren't the big thing at that point. And so I applied to grad school out of undergrad because that's what you're supposed to do, and I didn't get accepted into any place. So this was kind of a bummer. Didn't know what to do. And I ended up getting lucky enough to see a talk by Dr. Jason Barnes, who's up at the University of Idaho. And he was talking about Titan and exoplanets, and it was very interesting. And so I emailed him and asked if I could work with him. Just I didn't have anywhere else to go, so why not? And he was nice enough to hire me on. And so that was really when I started working on exoplanets. And I worked on an exoplanet called HD 80606b. I know, it just these names. But this planet is very interesting because it's very eccentric. And so it eccentric means that instead of a nice circular orbit, it has an ellipse orbit. And this is to the extreme that it would look like a comet. So this planet goes out to almost where we are around Earth's orbit, and then it cruises past its star closer than Mercury. So this planet gets extreme heating and extreme cooling, and all these really neat things happen with it. And so I studied this planet for a while, and I really got that exoplanet, like, yes, this is what I want to do. So I knew this is what I wanted to do. I applied to grad school with this newfound passion of this is exoplanets, and I didn't get in anywhere. So yeah. So from there, I decided to pursue a master's degree at San Jose State, where I got my master's degree in physics, and I continued to study exoplanets. This was actually at the time that the Kepler Space Telescope had launched, and so they needed somebody to do data analysis and look through the light curves for anything really wonky that was going on. So I worked on Kepler for 3 years after that, and I was really, again, I graduated, I was super excited. So I figured, why not try one more time to get into a grad school? And so I applied everywhere, tons of places, and I got into CU. So I went there. So it took a few tries, but I ended up going to CU. And from there, I've worked with both Dr. Jean-Michel Desert, who ended up transferring to Amsterdam, and then also with Dr. Zach Berta-Thompson. And from there, I've just been working on exoplanets ever since. So it's been I knew I wanted to do exoplanets. It's just trying to figure out where to go. So I guess I don't want to say the moral of the story is keep trying if you didn't get into a grad school, but it happens to people that not getting into grad school does happen. It's hard and it's frustrating, but just keep putting yourself out there and doing what you love. And I don't want to say things will work out, but just do what you love. And regardless of where you end up, at least you're doing something you're passionate about.
Yeah, talk about perseverance. That is awesome. Congratulations on your,
Thank you.
on being you're finally here and you're doing, what you love to do. And it's nice to hear that, through all of that, you're still here doing what you love. You never changed paths to say, okay, well, I have to, I have to make something work. So I'm going to, go do this other thing that I'm not really interested in, but is guaranteed. And so that's awesome. That's a great story. Thank you for sharing that with us.
Yeah.
Um, what sorts of skills? So, along this path, you probably learned a lot about, what was important to, when you're applying to grad schools and working with researchers. What sorts of skills does one need to have to study exoplanets?
I would say the biggest thing for exoplanet science is to have imagination and creativity. I think that we are discovering alien worlds, and as that implies, these are planets that we just don't have on the solar system. So having that imagination to try to picture what could be going on these planets that we're just not seeing on the solar system. Why when we see a planet on an 8-hour orbit around its star, what could it look like? Could we picture a bubbling hot magma ocean on one side and a rocky, cold, desolate surface on the other? So really just having that ability to get creative about these things, I'd say, is the big one. And then with the imagination, the creativity, just having excitement for this, right? We always see the end results when we talk about exoplanets, these cool things, but there's a lot of work that goes on with all of that, and doing data reduction and trying to tease out the smallest of signals. We're talking like 10 to the -4, 10 to the -5 type signals, which is just really small. And so having that, both the patience, the excitement to keep going, and also just the perseverance to try to keep going at this, is something that is not really talked about, but I really recommend having. And so with the excitement, you will have that perseverance to get to the end result. So I think those are the big ones.
Well, it's obvious that you really love doing what you do.
I
So
do, yes.
that's pretty awesome.
I love that you put imagination first. Like that's my favorite thing about teaching people about exoplanets is to be like, look how weird this thing is. Okay, now look how weird this thing is.
Yeah.
They're just crazy.
It's exciting. And I love talking to people about exoplanets, because I find sometimes even my imagination is limited. I work with data and everything, and slowly, like that, you kind of get into a box of thinking, and then you talk to someone and they're like, but what about this crazy idea? And the crazy idea is not because it doesn't make sense, but because it's something it was so out of the box that I'm not used to thinking, and I'm like, hey, that could work, and I get really excited about this. And so it's amazing when you talk to people. Everybody has a different viewpoint and an idea, and that's the great thing about exoplanets.
So in talking to people about exoplanets like you do you have a perhaps favorite exoplanet misconception or something that comes up a lot that people are just a little bit off with?
Um, oh,
I'm sure
that
it's
is
hard because there's
that
so
is a
little that
tough
we
one.
actually know.
Yeah, yeah, that is a tough misconception. I don't really think so, because I feel like a lot of these there's not really misconceptions. There's just a lot of unknown things. And I've noticed that, maybe you're not understanding one thing the way we know it, but that's not to say it isn't wrong, is sort of the way I guess we would think about. In terms of facts, I think it's very interesting that we have yet to find a solar system like our own. Like that is really something interesting. We started looking for exoplanets when we looked for the first exoplanet. Okay, so we found the first exoplanet around a sun-like star was found in 1995. But the reality is, our instruments could have found these exoplanets way back in the 80s. But that was because we were looking for solar systems like our own. And instead, what we discovered were there were planets that were right next to their stars, which puts out a bigger signal. We just didn't know that that's where the planets were. And so I think a fun fact about that is, everything we thought we know going into exoplanets, we realized we had no idea of what it's all about. And the more we discover, the more we realize we really don't know that much. And I think fact-wise, that's just the fun thing about exoplanets.
Like a lot of astronomy in this whole science, I feel like it's a very humbling field, that every new paper that is published makes you just think, wow, we know nothing about any of this, and there's so much to learn.
Yeah, it's basically the definition of science. and that's why I'm very excited about this field.
So I guess now we can transition into part 2 of the interview. This is a fun little thing we like to do called Capcom Q&A, where we're going to ask you some questions submitted by the public, and hopefully you can they're not scary. You should be okay. Didn't mean to spring it on you.
I love questions.
I'll let Colin go first.
Thank you. So, sorry, my Google Docs just signed out. It just said, you're signed out and you need to sign in to see this document. And I was like, thanks, Google Docs. Our first question comes from David in Austin. And David is asking, what's the furthest away that we've found organic compounds?
Oh, that is a great question. Okay, this can mean a lot. Organic compounds in in the sense of thinking about life in general, so the building blocks, I don't believe we found complicated organic compounds outside of our solar system. So Titan is a perfect example of where you would want to go to find the building blocks for organic compounds. If you're talking just in terms of, say, methane, we have, I believe, it's slightly debated if we have or not, but I believe we have found methane on some gas giants. And I don't know the distance, but think about 100 light years or beyond. So methane, we do know methane is out there, which means that methane interacts with light. So it's likely that these planets have organic compounds in their atmosphere. But if you're asking is in terms of thinking about building blocks of life, I would say we're still stuck in our solar system for that.
So you're theorizing exo-cows is what you're saying.
I am thinking about it. The methane has to come somewhere.
Love it.
Ray is asking, how hot is a hot Jupiter? And then I'm asking also, what is a hot Jupiter?
Yeah. Hot Jupiters are, if you took Jupiter and you moved it next to our sun so that it orbited every 3 days. So Mercury is about 88 days, so right on top of the star, which it was actually one of the first planets we found, are hot Jupiters, because they are just really easy to find. They tug on their star because they're right next to their star, so you see that signal and it's really large. So that's a hot Jupiter, and these hot Jupiters at 3 days, as you can imagine, are very hot. Most hot Jupiters are probably around 1,000 to 2,000 Kelvin. There is actually a hot Jupiter called Kelt 9b, which orbits right next to a really massive star, what we call an A-type star. I don't remember right off my head what the mass is of the star, but it puts out so much more heat that the temperature on this planet is somewhere around 4,000 K. It is actually hotter than the cooler stars, which just, as you can imagine, is a whole other thing of physics that we're still working to understand.
That is, again, one of those things that just shatters your intuition. I'm thinking, wow, there's these Jupiters that are hotter than some stars.
That's right.
I was about to jump in with the next question and my mind just went like a whole other direction. Like, what if?
Exactly. I love what if questions because that is exoplanets.
That's awesome. Another question from Ray, and this might be sort of a subjective one, but what has been the most important exoplanet discovered so far?
Oof. Wow. Let's see. This is very subjective. I would say the first one around the sun-like star, 51 Peg B. That really started the whole field. It made us realize that there are other planets out there and that these planets are nothing like our own solar system. And I think and where it was located right next to the star challenged everything we knew about how our solar system formed. And so it really I would say was the start of everything, and that's why I would say it would be the most important, because without that discovery, this field might not even exist. I mean, we would eventually find planets, but that planet is what started it.
That seems like a reasonable, most important exoplanet discovery to me. So,
and I believe they won the Nobel Prize last year on that discovery. So, just to highlight the importance of that. Yeah.
Very cool.
Well, that wraps up our Capcom Q&A. Those are the questions that we have for you for today from the world of.
Thank you everyone for submitting questions. And I'll just butt in really quick. If you have any more questions about exoplanets after listening to this podcast, I believe you have my information. I'm Jessica Libby-Roberts, and you can look me up on the the website at CU for my email address, and feel free to email me with any more questions that you might have.
Take her up on that. This is a pretty cool offer. A scientist saying, hey, I'm opening the door to any and all emails for questions that you might have. This is pretty cool. So don't slack on the questions, people.
Do you mind if I tell one quick story about where the cotton candy came from? Like that notion of cotton candy density?
Not at all. Go for it.
Okay, just because it's kind of funny. So when I was presenting the 0.1 grams per cubic centimeter, I would announce this in talks and during meetings, and everybody would be like, wow, cool, I guess that's low density, but is it? I mean, these are scientists, astronomers, but trying to visualize it was so weird. So I realized that I needed to come up with something a little bit more that was easier to visualize than just a number. And so I tried marshmallows. I went out and measured their densities, and I found that they were too dense. I attempted to put a marshmallow in the microwave to make it fluff up some more and measure the density, but it exploded. So that I knew these planets weren't exploding. So that's not a great analogy. So then I tried cotton candy, and I went to the candy store and I bought a bunch of bags of cotton candy. And she asked me if I was throwing a party, and I was like, no, this is in the name of science. And so I went back with the other people in my group, and we sat down. We measured the mass and the size of the cotton candy, and we actually discovered it was just slightly under the 0.1 grams per cubic centimeter, and that's sort of where we got the idea to say cotton candy planets. And so that really helped, because after that talk, when I had mentioned that, then you would see everybody's eyes like light up and be like, whoa, that is weird. But until then, I needed to find something. And of course we ate the cotton candy afterwards. So science is both very exciting and tasty.
I like it.
That's a great story.
I had to
That's
share
awesome.
that because where did that come up, kind of thing. It's fun.
Well, and that's kind of cool, because I've heard, super puffs mentioned before, and this idea of that they are like cotton candies. So you've coined this term now in the
I did, yeah.
astronomical community. That's pretty awesome.
I did, and it makes for a great joke during talks and everything. So
Yeah.
it worked out really well. But yeah,
I love the idea of just like a whole bunch of really serious scientists poking at different candies,
Right.
seeing which ones have the right density.
Yes, and don't put marshmallows in microwaves for very long. Like, don't walk away and come back, because it's just awful.
I remember in an 8th grade chemistry class, we put Peeps in a bell jar and kind of had the same reaction.
Yep.
Peeps in a vacuum. Huge.
That would be fun to see. That would be really fun.
It really was.
I think I did the same experiment, Tara. It's it's
science is very serious.
It is. Only serious people here in science.
Oh yes.
All right, and this has been our conversation with Jessica Libby-Roberts. Jessica, thank you so much for being on the show with us today. It was really fun hearing you and your passion about exoplanets. We really appreciate your time.
Thank you for having me, and I always love the opportunity to talk about exoplanets.